how they help each other. So let me start with this quote from Jeff Bezos, founder of Amazon. The most important single thing is to focus obsessively on the customer. Our goal is to be Earth's most customer-centric company. So Amazon is obviously very customer-centric. They're also at the forefront of AI and machine learning development. However, when I looked at the current practices for developing machine learning models that most of us machine learning developers use, I'm actually not sure that we are very customer-centric. Like, is the way we develop machine learning models customer-centric? Is the evaluation processes and the metrics that we use to evaluate models, are they really customer-centric? Well, I'm not sure. So what I'm going to talk about today is how we, AI and machine learning developers, can become more customer-focused. And I think, as you can guess from the title, A/B testing has something to do with that. So this is the outline that I'm going to follow. I'll give you a quick introduction to A/B testing. Now, most of you probably already know what A/B testing is, but just so that we are all on the same page, I'll give you a few examples of real experiments, then discuss a little bit why should we A/B test AI system, why kind of offline evaluation and metrics that we normally use is not enough. And then finally, I'll share 5 pitfalls and lessons that I learned when I was applying A/B testing to AI models. All right, let me start with the introduction. So this is a true story that happened in Bing in the beginning of 2012. Just get a laser pointer. So an engineer in Bing had an idea, and the idea was very simple. He wanted to take first sentence from the description of the ad and put it into the title. So it's actually a very easy change, a few lines of JavaScript. However, this was one of the hundreds of ideas that were there in Bing, and compared to many other ideas, this one seemed like nothing special. Right? So as it usually works, the idea was put in the backlog, and it stayed there 1 month, and another month, another month, another month, and another month. And after 6 months, it became clear to the engineer, like, this is never going to happen, right? So there are many features that ranked above this idea. It's just never gonna make it. But then he thought, this is like trivial, just a few hours of work. Yeah, so he just did it in his own time and started an A/B test, which is kind of the culture in Bing, that anyone can propose things, and as long as you run them through an A/B test, you're good. So he started an A/B test, and something strange happened. Immediately, an alert fired. And that alert said, something is wrong. We are making too much money. Like, this cannot be true. Which is actually the case, that perhaps 99 times out of 100, when something like this happens, it's actually a bug. Something is wrong. Like, we forgot to show the web results and only ads, and people are clicking on them, and that's why the revenue is high. But in this case, there was actually no bug. This idea increased Bing's revenue by 12%, which at that time was over $100 million a year, a lot more now. And it also didn't really hurt any user experience metrics. So what is the lesson from this story? The lesson is that we are pretty bad at assessing the value of our ideas. Like, this was perhaps the best revenue generating idea in Bing's history, and no one recognized it. And it was just put in the backlog and stayed there. And if not, this engineer would never get implemented. And the same actually true in the opposite direction as well. And I was at Microsoft, we ran a study, again in Bing, and we found out of those ideas we do get prioritized and implemented, actually only 1/3 of them are good for users and business. And 1/3 is neutral, and 1/3 turned out to be bad. So this is actually really humbling. Suppose you have an idea how to improve your product, you think it's great. Well, it turns out in reality, your idea is as likely to hurt users as it is to actually help. And this is true not only in Bing, many other software countries, and not only in software engineering. In sales, where I work now, there are lots of contradicting best practices. Like you can search online, what is the best day to contact a cold prospect? And you'll find recommendations and different justifications for every single day, right? And in medicine, where it's really important that we correctly evaluate an idea because it's perhaps a matter of life and death, not just making a little more money, FDA, EMA, they do not trust expert opinions. They mandate what they call randomized controlled trials, which is essentially A/B tests. There's also the reason why we still do not have a COVID vaccine. It's going through the trials. Okay, so what is the takeaway from all of this? The takeaway is that we can't trust our gut. If we want to make the right choices, the right decisions, we need data from real users. And the best quote that I know, which kind of sums it up, is this one from Admiral Grace Hopper, the first woman admiral in the United States, who said, "One accurate measurement is worth 1,000 expert opinions." All right, so we want to use data, but now we also need to know how to use the data. Should use the data correctly. So I think everyone knows this quote here, this saying that correlation is not causation. But I am still amazed how many people, even those who know it, still use correlational data in causal way. And the argument usually goes like this, that, well, correlational data is the only data I have. So using some data is better than using no data at all. So I'm going to interpret this correlational data in causal way. And I wanted to kind of warn you that this is a very dangerous practice. And let me just show you this kind of fun hypothetical example of what may happen if you do this. So I live in Seattle, and Seattle is known for its rain. In fact, it's raining right now outside of my window. And I don't really like the rain. So I sit in my house, sort of look at this gloomy weather. And one day I make a very interesting observation. I notice that whenever I see people on the street carrying umbrellas, very soon it starts raining. And then I have a revelation. What I can do is I can bend the umbrellas, and then the rain is going to stop. Yeah. Okay, but of course, this makes absolutely no sense. Bending umbrellas is not going to stop the rain. However, it will actually make everyone a lot more wet. Yeah, so the takeaway here is that if you rely on correlations, it's not just going to be neutral, it may actually be very harmful. All right, so how do we use the data correctly? Well, the best scientific way to evaluate an impact of your idea on your business is A/B testing. And this is kind of in one slide how the basic A/B test works. Suppose we have users who are coming to use our product, for example, our website or our mobile app. What we are going to do is we will randomly assign them into two groups. The first group, we'll call it control, will just get to use our normal system, our normal site. And the second group, we call it treatment, they will get to use our system with some modification, with that new feature X. And that new feature X is our idea that we want to evaluate. So we let this experiment run. Users will be using these two different versions for some time. And during the time, we collect the data. And then at the end of the experiment, we use the data to compute metrics and determine the winner. Now, what's the nice thing about this process is that if at the end of the experiment, we actually see differences in metrics, then it can really only be due to two reasons. The first reason is that it was caused by our new feature X, because everything was running at the same time, the users were distributed randomly, there is no bias of any kind. So it must be caused by our new feature X. So that's one explanation. And the second explanation is, well, perhaps it's just due to random noise, because just by chance, somehow we got maybe better users in the treatment in control. And to get rid of this random chance hypothesis, we do statistical testing. So if at the end of the experiment, we see a statistically significant differences in our metrics, then we can, with reasonable confidence, conclude that it is indeed, this difference was caused by our new feature X. So this is how A/B testing works. Now, if you note, there are many other names for A/B testing. You may see controlled experiments, randomized experiments, randomized clinical trials. So they all mean the same thing. And there are also more complex variants of A/B tests. For example, you can have multiple treatments, an A/B/C test, as well as some other designs, but the basic idea is the same. And then finally, we must run statistical tests at the end, not just look at the metrics, because we want to make sure that the differences are not due to chance. And again, why do we like A/B testing so much? Is because A/B testing is the best scientific way to prove causality. There are other ways as well, but they are not as good, not as sure as A/B testing. All right. So what can A/B testing be used for? Well, many different things. And let me just show you a few examples. This is one example from Outreach, where we can use A/B testing to test different sales email templates. We can use A/B testing in search. I already gave you some examples from Bing. For example, in this case, this is an example of an A/B test where we are trying to determine how many search results should we show on a page. Should it be 10? Should it be 8? Maybe even fewer. And you can use A/B testing in an operating system. This shows an A/B test that was run in Windows when Windows 10 launched to test what text should be in that search box in the bottom left corner if you have a Windows machine. And A/B testing can be used for many other things as well. All right, so now that I've hopefully showed you that A/B testing is a great thing to do, let's discuss, should we really A/B test our ML models? Why should we A/B test machine learning models? Because after all, we actually have a pretty good evaluation process for machine learning models. We have our training tests and test sets, holdout sets, cross-validation. We have many metrics, accuracy, F1 score, ROC, and so many other ones, which actually help us evaluate how ML models work. So why is that not enough? Well, let me give you 7 reasons why, my top 7 reasons why this kind of offline evaluation of machine learning models is not sufficient. Reason number 1 is that your train and test sets can get old pretty quickly. And even now the model may be working really good on them, when you deploy it into the real world, well, the world has changed. Now your model getting a different type of data and may not be performing as well. The second reason is that sometimes training and test sets may miss entire classes of examples. Now imagine you're training a ranking algorithm for a search engine, and somehow you forgot to include weather queries, queries about the weather. Well, most likely your model is not going to work really well on those weather queries. And this is also particularly important if you want your algorithms to be inclusive, because generally it's the majority use cases that get represented very well in the training and test sets. And then the kind of interest on the minority groups of users are the ones that sort of either get underrepresented or completely ignored. And as a result, your model is going to do great for majority of people, but actually not so good for minorities. And if your goal is to create an inclusive model, this is not good. Number 3 is that labels produced by human annotators may be inaccurate. And a great example of this is what I remember we did back in Bing, where we would often show different designs of new experiences for the search results page to users. And what we found is that users always pretty much preferred the experience with more images and more videos, kind of richer content experiences. However, when we tested those experiences in the real world, they would almost always lose. And the reason is because in reality, people are busy. They want to complete their task as fast as possible. They're not just there for entertainment. And all of these images and videos just get in the way of them completing their task faster. Now, reason number 4 is that all errors are not equal. The common practice is that we kind of treat all errors the same most of the time when we evaluate our machine learning models. But for real users, some errors may actually be a lot more important, and some of the errors may not be important at all. And it's very hard in an offline setting to actually figure out what is the segmentation of different types of errors and how important some errors versus some other errors. In order to do that, you really have to expose this experience to real users. Now, number 5 is that UI matters. The machine learning model is really just one part of the whole user experience. And it may have a big impact on how the results are perceived by users. For example, if our model tends to make errors in certain types of scenarios, we know it's not as good in certain types of scenarios, well, we can make up for it in the UI by making it easier to reformulate and correct and explore kind of the space of possibilities to just help users navigate through those issues. And on the other hand, if you don't think through the UI, it may actually emphasize the errors more and really put users into kind of an undesirable situation and mislead them in some way. Number 6 is that model is a part of a bigger system. For example, the output of your model may be an input into another model, which is very common. We sort of chain multiple models together. And even if you improve your model, if in the process you actually somehow substantially affected the distribution of the different types of errors that your model produces, on average it's better, but it's actually now it's different, then the downstream model may actually degrade, because it's already been kind of tuned to the old pattern of errors that your model used to have. And then finally, and probably most commonly, most importantly, your model implementation may have a bug. In the development environment, the model may work great, But as you deploy it to production, a lot of things may change. Somehow some parameters may get tweaked. Maybe the input data is somehow a little different than what you were expected in the development environment. Or data is the same, but the parser of the data has some issue. It's a different parser that's used in production and in development, and all kind of reasons like this may end up in your model actually not performing the same way in production as it was in the development. So what essentially all of these points are saying is that we can't really just be satisfied with evaluating our model offline. We need an online evaluation, which, and the best way to do that is to run an A/B test. And what this allows us to do is to create this virtuous cycle where we use A/B tests to evaluate our model in an online setting, and this allows us to measure the end user, the ultimate impact of our model on user experience. But what we get in return is we get all these learnings, feedback, and new ideas. So things like mentioned here on the left, those kind of insights into model performance that you can't really obtain from an offline evaluation. You can only get it from online evaluation, and that will help you improve the model and make it better. So it creates this virtuous cycle with users in the middle. So making our model development a lot more customer focused. All right, so now hopefully I've convinced you that it's a good idea to A/B test your ML models, and all of you want to go and start doing this if you're not doing this already. So as you start A/B testing your AI models, there are certain specifics to it, and there are some pitfalls that are good to be aware of. So here are my 5 kind of top pitfalls from my own experience of doing this. And I'll tell you about each one of them in a little bit more detail. Now, before I go to the pitfalls, I'm going to be using examples from outreach to illustrate them. So let me give you a little bit of a background so you can understand those examples better. So what is outreach and what we do? So outreach is a sales engagement platform, which means it's a software that sales reps use to help them as they reach out to prospects and customers. And the way it works is that managers can encode the sequences of activities they want sales reps to take, like this example here, when reaching out to a specific persona, and then outreach will have kind of orchestrate and automate the execution of this. And in the process of it, we use machine learning models really for 2 purposes. One is to optimize those sequences, to make those sequences better. And the second is to help the sales reps personalize and just better respond to a certain, take better actions in a certain situations, especially in a difficult situation that they are facing. So the examples that I will show, I will be in that sort of recommendation space, where at a certain point we are going to recommend the sales rep what they need to do. All right, so now let's talk about the lessons. The first lesson is that AI versus no AI tests are tricky. And the scenario here is that you had a system and now you want to introduce a machine learning model into it. An example from outreach here is that we may decide to develop a machine learning model to recommend the sales rep a best content, say email template, that they can use to respond to a certain email from a prospect. A sales rep receives an email from a prospect, will recommend what template they should be using to respond back. Yeah, but the problem is that as we put in that machine learning model into our system, it may have some side effects. And most common side effect is the performance, because all of this is running on the same servers. that there are now other components of the system are getting delayed. So the problem this creates is that when you run an A/B test, the result that you see is a combination of the impact of the model, the recommendation model, and those side effects it's causing on other components. And ideally, you want to disentangle those. You want to understand them separately and then solve them separately as well. So how to deal with this problem? Well, the solution that I recommend is to run an ABC test. So to have 3 variants. The first variant would be our control. Essentially, there is no AI, just our standard process. The second variant is very interesting. I called it a hidden AI. What we are going to do is we'll actually run our machine learning model in the backend, and we get the results, but we are not going to use the results. We'll just throw them away and still have the same normal experience. And then the third variant will be our full AI. We're going to run the machine learning model and also use the results to make recommendations. Now, the advantage of this setup is that when we compare A versus B, we only, because the user experience is the same, the differences that we will see are only going to be those performance impacting side effects that introducing the model has created. And when we compare B versus C, the only difference is going to be the model and the user experience, because both B and C have the same side effects. And then when we compare A versus C, it's the full effect. So when we design our experiment like this, we can actually separately measure these 2 pieces and then address each one of them independently. Okay, lesson number 2 is what I call to ensure equal learning opportunity. And this applies to the models which learn and adapt on the fly. And for these models, their quality depends heavily on the amount of data that they see on an ongoing basis. For example, our Web Content Recommendation model may be getting retrained on a daily basis based on user feedback, as well as some new content that gets created. And here, the thing that we need to be careful about is that the variant that has a larger fraction of users, say if our treatment has more users than control, or vice versa, that variant with a larger fraction of users will get more data for model training and may perform better, not because the model is better, but just because it sees more data. Now, the solution here is pretty simple. We really need to ensure that treatment and control are exposed to the same fraction of users. And there is also kind of an interesting caveat that I've seen happen, that if the test that we run is not a 50-50 test, and we are not using the full population and breaking it in half, but we are just using maybe 10% versus 10%, then most likely our default population, which is not in the experiment, is going to be using the same model as our control population. And we need to make sure our control model is not going to use the data from the default population for training. So make sure it does not share the data. All right, lesson number 3. What also often happens is that a machine learning model targets a specific narrow scenario. For example, when we introduce our content recommendation model for sales reps, we may initially only target one specific type of emails, cost objection. If the prospect replies something like, I don't have enough budget right now, it's COVID time, budgets are tight, then for this kind of email, we're going to give recommendation. But if they're going to reply some other types of objections, we are not going to give any recommendation. Now, the problem here is only a subset of deals would face a cost objection. And if we then evaluate the results all up, for example, we may want to measure how many meetings with prospects did that rep book. And if you look at just all of the prospects, including those who did not provide a cost objection, then that signal may actually be very much diluted in the noise of all of the other deals that the rep is handling. So the solution here is to do what is called triggering, which means restricting our experiment analysis only to the affected population, only to those who actually, only to those prospects who actually exhibited, shown cost objection. The problem, however, is that it's not so easy often to determine what is the affected population. Now, in the treatment, it's usually pretty easy. These are the people to whom we showed recommendation, right? But in the control, we did not show any recommendations. So how do we know who is affected? So in order to do that, we often need to introduce what's called counterfactual logging, which is essentially say that I want to find the prospects in control who, if they were in the treatment, we would have shown recommendations for. So there's this kind of counterfactual argument. And one of the best ways to do this is actually to just run the model in control as well, and log the situation where it's going to trigger a recommendation, but not use the recommendation. So again, that's kind of a hidden AI type of setup, ABC design that I shared in lesson 1. All right, lesson number 4 is to beware of side effects. It's kind of the opposite of the previous one. So here, the situation is that we are introducing an improvement to an existing machine learning model targeting a specific scenario. However, that may, even though it improves that specific scenario, it may inadvertently affect positively or negatively other scenarios. Right? So suppose we have our content recommendation model, which is doing great for cost objections. Now we want to add another scenario, which we'll call not the right time. Now, when the prospect replies, well, now it's not a good time to discuss, I'm busy, get back to me in 3 months, and then maybe we do something. Now, while introducing that scenario, we may actually inadvertently, because it's the same model that we use for both scenarios, we may inadvertently hurt our cost objection scenario. So how do we detect that? Well, here the solution is kind of the opposite from triggering. Triggering helps us zero in on a subset of a population, but here we want to look at all the populations. So we want to do an all-up analysis. We also want to have a large, comprehensive set of metrics, not only metrics that apply to your scenario of interest, but also many other metrics which evaluate other different scenarios. And we also may want to segment our population in different ways. For example, we could segment by scenario or by persona or by industry in the sales case. Now, all of this will then help us to kind of catch any unexpected, surprising side effects that our experiment may generate. Now, one issue with this is that we'll suddenly be running a lot of different A/B tests, maybe tens of thousands, even hundreds of thousands, not A/B tests, hundreds of thousands statistical tests for all of these different metrics and segments and different combinations. And that may result in false positives. It's an issue called multiple testing. And there are different ways to deal with this. The simple way is you use a much higher threshold, statistical significant threshold, but there are other ways as well. And if you do kind of this widespread evaluation, you should use some of those tests. Otherwise, you'll just see false positives, which are most likely will not actually lead you anywhere. And finally, the last lesson is to measure the full machine learning pipeline. And the situation here is that often we string multiple machine learning models together to produce the final result. And we really, to maximize our learnings, we really want to understand the impact of each part, not just the end result. So an example here is that our rep content recommendation model may consist of the 3 different models. There may be, say, a named entity recognition model, which will try to detect some known entities, such as mentions of a competitor in the email. Then there's a scenario detection model, which would determine what kind of objection it is. Is it a cost objection? Or is it not the right time? Or is it something else? And then finally, there is a recommendation model, which takes as an input the first 2, as well as the text of the email, and then recommends an email template. And ideally, we want to know the impact of each piece. Now, this is actually not very simple and somewhat use case dependent, but the general approach is that we want to first create a login for each one of these models to log the results as well as the confidence levels. And then we can introduce kind of carefully designed segments which are based on the confidence and prediction class. For example, if we are evaluating our recommendation model, we may want to introduce segments based on the confidence of the scenario detection. And then we can see that based on different levels of confidence we have in our scenario, how well do our recommendations perform. This is now a little bit tricky because in order to do this, the assessment of confidence need to remain the same, which means ideally we do not change our scenario detection model. Because if the confidence changes, it results kind of in unequal comparisons there. All right, so this is, I think, all that I wanted to say. So what are the takeaways? If you remember just one thing out of my talk, I would say let it be this first bullet point here, that we as humans are very bad at assessing the value of our ideas. So don't trust the experts, don't trust yourself, just get the data. And A/B testing is the best scientific way to use the data to measure the causal impact of your model on users and business. And as I mentioned earlier, kind of traditionally A/B testing is associated with UI, but it's really not just for UI. And in fact, you can and you should A/B test your machine learning models. It will both provide you deeper insights into your model performance and may save you from embarrassment. You deploy your great model and it performs horribly in the real world. And as you start A/B testing your machine learning models, there are these 5 lessons, 5 things to keep in mind. AI versus no AI tests, equal learning opportunity, zeroing in the target scenarios using triggering, evaluating side effects, and then measuring full machine learning pipeline. All right, so this is all that I wanted to say. You're welcome to connect with me on LinkedIn. And let me now answer some questions. So feel free to type questions.
Yes, great. Thanks a lot for the great presentations. I see we have quite a few questions in the Q&A. You can open up, or you want me to read to you?
Yeah. Yes, let me. All right, so I think I can just go through these questions in the Q&A. So how do you know if 2 factors are correlated or causal? So I think this is from earlier in the talk. So I think this we answered, right? If you have a properly designed A/B test, it will show you the causal impact. If you just look at the data, it's generally would be, you would not know whether it's correlated or causal. Okay, the next question. Sometimes people split audiences and make decisions based on means and standard deviations. Is that a good approach for A/B testing? If not, what would be better? Yeah, so there is, we didn't go in this talk into how to do the statistical testing. There is kind of a standard approach called hypothesis testing, where we assume that there is no difference, and then we look at the data, and then we compute this quantity called p-value, which will show us kind of how unlikely it is to see this data or a more extreme data, given our assumption that actually there is not supposed to be any difference between treatment and control. But that's just one approach. There are also many other statistical tests that could be used. In my experience, it's less important what kind of statistical test you use. Essentially, if you have a strong result, strong signal, any statistical test is going to show it to you. And if the result is very weak, then there is a difference between different tests. But if the result is very weak, the difference is small, you may not even care that much about it anyway. So it's less important what decision you make in that case. So yeah, there are many ways to do that. But if you want to see one way, you can look up hypothesis testing online and read about it. All right, next question. Will multiple comparisons in ABC tests make the false positive rate go up? So eventually you get a good variation, even if it is not. Yeah, so I think I've mentioned probably a little bit later when this question was asked, that yes, you need to be careful with multiple comparisons. If you have a lot of metrics, a lot of segments, in an ABC test, you essentially just add in one extra. You just have twice as many comparisons as before. It's not as critical, but as you start adding lots of metrics and lots of segments, that's where you really need to be careful. And again, for different types of approaches to statistical testing, there are different ways to deal with this multiple comparisons problems. For example, the Bayesian approaches we just completely avoid that. But the simple way that I've seen in practice work very well is, I think what Vasily mentions here, is essentially Bonferroni correction. For any extra test, you just divide your p-value by the number of comparisons. So you end up having kind of your significance threshold and them being a lot lower, which means that only sort of real true effects will likely pass it. So that's one way. And another way is there is just kind of a common sense that you need to apply as well, because often you are expecting, the metrics are not moving at random in your A/B test. They move in certain patterns. For example, I remember when we were doing A/B tests in Bing, we already knew how a relevance improvement looked like. It means that those 5 different metrics are going to move up and those 3 other metrics will move down. And there is just kind of a pattern in user experience. And if you see something that does not follow the pattern, then you could be very suspicious of, this may actually not be true, and you can look at it deeper. All right, next question. What if it is costly to run A/B tests? For example, it's expensive to ask doctors to label images. How would you design A/B tests to account for these costs? And there are some answers: larger funding request, label in the least expensive way. So yeah, I think design of A/B tests is kind of its own very interesting topic. What my experience is that in this kind of scenarios, there are many there are simple kind of A/B test scenarios, and what I talked about are maybe more of the simple ones and maybe a little bit complex, but with some of these recommendations I mentioned, you can get around them. In more complex scenarios, you'll need to be more creative in how you design an A/B test. Like it's hard for me to kind of think right away what would you do with, labeling images, but one thing that you could do is you would actually evaluate your results not based on how the images are labeled, but based on some kind of a later outcome, or based on, for example, how often doctors would use and decide to use or not use something. So you can kind of have those indirect evaluation measures where those metrics are easier to compute. So it's a domain dependent, but my experience is that in many of these complicated situations, you can actually figure out a way to run an A/B test. It's kind of in the beginning may seem like, oh, there is really no way, how would I do it? Then you think a little more and there is some way. Now, if you have any specific situations that you are dealing with, feel free to ping me, connect on LinkedIn, we can discuss. All right, next question. How should we decide how wide the experiment should be? How many people to, I guess, maybe to recruit in the experiment? So essentially as many as possible. However, if there is a cost, if there is a substantial cost in recruiting people, then there is a formula that you can use. You can do a power calculation, which depending on what is kind of meaningful impact for you is. For example, you may want to say that I care about more than 5% changes in this metric of interest. If it's less than 5%, I don't care that much. Or you can say 1%, I really care, less than 1%, not that important. And based on that, as well as on the characteristics of your metrics, like standard deviation, you can actually compute how many people you need to detect the change with high probability. So that's if it's expensive to obtain people. But if it's not expensive, for example, if it's an online situation, then my recommendation is always to essentially use your full audience, 50-50 test. You can start a little smaller in the beginning if you're not sure whether you're, maybe you're afraid that your treatment may be really bad and you immediately show it to 50% of people, they're gonna leave. But once you kind of confirm that things seem to be okay, ramp it up to 50-50 and use as many users as you can, because that will give you results the fastest, and then you'll be able to complete your test, get your answer, and iterate on your ideas in the fastest possible way. All right. Another question, can you provide some getting started pointers for A/B testing for ML? So frameworks, libraries, software tools. How do you usually implement components? Oh, okay, I think I skipped. I'll come back to that other question. How do you implement components needed by A/B tests? This is actually a great question. And this is one of the, I think, problems that's kind of hurting a little bit the evolution of research on A/B testing, is that I don't think there is a very good open source A/B testing tool that you can just get it, install and use it. There are some tools out there, but none of them really, at least based on sort of a few months, about a year ago or so, when I actually was looking at it in detail, because we were deciding what are we going to use at Outreach, and we were not happy with any of them. And the big companies who actually kind of advance the state of the art in A/B testing, like Microsoft, Facebook, Google, Booking.com, and a few others, they have their own internal built-in-house A/B testing platforms. So unfortunately, I can't really recommend good open source frameworks. If you're planning to start using A/B testing in your product, I would also not recommend to build the system by yourself, not at least until you actually ramp it up and say your organization is running hundreds of, maybe thousands of tests simultaneously, at which point it may make sense to invest into in-house tool. The problem there is that it seems simple. A/B testing seems very simple conceptually, but as you start implementing it, and especially if you want to implement some of the more advanced ways of like allocation and interaction detection and avoidance and detecting sort of bad experiments and things like that, it gets actually very quickly very complicated. Now at Microsoft, it's used to be a 100-person team, which was working on A/B testing platform for many years. So I would say you get one of the vendors, which is probably not going to give you all the details that you need, but they will get you started very easily. So there are companies like Split, LaunchDarkly, Optimizely, and others as well. All right, now coming back to the question above, can you use reinforcement learning for A/B testing? For example, contextual bandits. So yes, I think I wouldn't say it's for A/B testing, but there are, I think, a class of problems where you can essentially your goal is to optimize something, and you can use A/B testing to kind of keep testing different approaches to optimizing, or you can also implement a reinforcement learning framework to do that. So yes, so this is possible, and you can also kind of design your A/B test in sort of that multi-arm bandit way, where you start with a lot of different treatments, and sort of over time you automatically converge to the winning treatment by kind of discarding the bad treatments as you go. And that's also, this is again another reason why A/B testing platform is difficult to implement, because if you may want in some scenarios use that kind of approach, that's another sort of a big complexity in implementation. But yes, it is possible. It is possible to use both there. All right. Another question. Is there any way to know how much time I should run an A/B testing experiment? Yeah, I think this is similar to the question before of how many people to use. Similarly, you can also compute how much time you need to run an experiment in order to get statistically significant results. This is, however, somewhat dependent also on the choice of your metrics. Because there are certain metrics that as you collect more data from users, they actually get more sensitive. The p-value goes down, but there are some metrics where usually the count metrics, for example, you're counting the number of, I don't know, purchases, you're counting the number of visits. So for those metrics, it's actually doesn't matter whether you run experiment for 2 weeks or for 2 months, because as you collect more data for that metric, yes, you get more data points, but the variance is also usually goes up, and your kind of statistical significance remain about the same. You don't actually get benefit from running experiments longer. And that's also the reason why I really recommend, if you have a choice about running an experiment with a smaller number of users but longer versus running an experiment with more users but shorter, you always choose running the experiment with more users and a shorter time frame. All right, do you have A/B testing framework, open source projects working well? Yeah, I think it's the same question. I think, so I don't think there is a very good framework. The best one that I can recommend is the project called Flagger. Let me see, I can maybe type for you in chat. Flagger, you can look it up. It's I think it's developed by the company called Checker. That's everything is in this R there, but that's kind of was the best candidate when I was looking at different A/B testing frameworks. However, it's not specifically designed for ML, so you would need potentially some modifications there, and it supports the basics. But there are, I think, there are some issues with trying to evaluate it. So some technical issues that you would need to solve. So we eventually decided to go with a vendor instead of Flagger. All right.
Great.
No more
questions? I think we cover all our questions. Thank you very much for that. We are actually over time a little bit, but for the last things, I want to give just a few minutes about the recruiting. I think I shared your team is hiring data scientist, machine learning engineer, and maybe you can just introduce say a few, about the positions and see if folks have any questions.
Yes, certainly. So we are hiring, we are growing our team at Outreach. We have a small team, we actually only about 10 data scientists and machine learning engineers. Currently, we are looking for more machine learning engineers. So really, I think the interesting thing why I went to work in the sales area, which is kind of not very common for data scientists, is that this is one space which has not yet been, I think, affected by AI and machine learning. If you look at how salespeople sell without Outreach, it's pretty much the same as you see in the old movies. It's like you get a list of people with phone numbers, nowadays also email addresses and LinkedIn profiles, and then you go. And there is just really no data is used. So this is a great opportunity to really transform the industry, transform the sales industry. And that's why I left Microsoft and joined Outreach. And I think our company is doing pretty well. Recently reached the unicorn status, growing very fast. So an opportunity to be part of one of the fastest growing startups in the US. I think we were called like number 4 fastest growing startup by LinkedIn, by Deloitte, I forgot. So some of those surveys, and be part of kind of a small but elite team.
Great. So are they only located in Seattle, or can also other cities or remotely, given nowadays the pandemic?
Yes, nowadays we can be remotely. We are located in Seattle, and think there is, once the pandemic is over, being in Seattle would certainly be an advantage. But for high-level experienced people, for junior people, level 2, senior level, we would require that you relocate. For principal level, you could work from anywhere. So for experienced people, you could work remotely even after the pandemic.
Awesome. Great.
So if you have any questions, feel free to ping me on LinkedIn about A/B testing, about positions. Very happy always to connect and discuss.
All right. Thank you very much, Pavel, for the great presentation.